So to pick up where we left off, we had found that if we're working with probability tree diagrams, to find the probability of a branch, so what happens at the end of the branch is an intersection of two events. So you're interested in the event in which two things happen at once, then it's as simple as multiplying the probabilities along that branch. Probability of the first event times the probability of the second event given the first event has occurred. So let me write that down because that actually is a very powerful formula or rule that we can write more generally as the probability of A intersection B is equal to the probability of A times the probability of B given A has occurred. And so to break that down, let's think about it this way. So what's the probability that both occur? It's the probability of the first occurring times the probability of the second occurring given the first already occurred or happened. So intuitively, it makes sense. So it matches our intuition. The thing is, this is a conditional probability right here. And it assumes that what happens to B will depend on whether or not A has occurred. So for that reason, we do have an independent version of this rule where we write the probability of A intersection B is equal to the probability of A times the probability of B. And this is special because what we're assuming here is that A and B are independent events, where A and B the occurrence of one happening doesn't affect the occurrence of the other. So this happens quite frequently, and we'll show an example right now of this happening. So we'll talk about the independent event version first. So imagine two coin flips in a row, independent of each other, and we can draw out the probability tree diagram roughly as the first flip has two possible outcomes. Head on the first flip or tail on the first flip. Each one has a probability of occurring of 1/2 or 0.5. Then, regardless of what you got for the first flip, there's still the possibility of a head or a tail on the second flip. And we'll denote this H1 intersection H2 and H1 intersection T2. The subscript in this case indicates whether it was the first or the second flip. And in both those cases, it is still equally likely for us to get heads or tails. And this is true regardless of which outcome you had in the first place. So to represent that, what we're talking about, so question, what's the probability of obtaining two heads or both heads? We know intuitively, we've already discussed and have worked with this sample space before, that this probability of H1 intersection H2 is 1/4 because there's only one outcome in that sample space where you get two heads. Namely, if we're talking about a sample space like HH, HT, TH, and TT, only one of those has two heads. That said, we can alternatively calculate it as knowing that we have independent flips, the probability of each one multiplied together. So if we have the probability of the first head is being 1/2 times the probability of the second one being 1/2, then we have, of course, that this is 1/4. So what about an example in which these are independent? So let's suppose our new experiment is to randomly draw 2 cards from a standard 52 card deck we observe each time if it's a diamond or not. So a diamond card is a classification by suit. There are 4 suits, so each card has a 1 in 4 chance of getting drawn as a diamond. So we'll represent this. And one really important thing here is we draw without replacement. What that means is if we're drawing without replacement, then when we take one card from the first stage, we don't put it back in the stack. So we've reduced our sample space. So here's how we can think about this. Let's draw the probability tree diagram. So first draw. And so we have 2 events. We have a diamond, we'll call A1, and not diamond, which is A1 bar. How many diamond cards are there in a suit? There's 13, and there's 52 total. So 13 out of 52, which is exactly equal to 1/4. On the other hand, there's 52 minus 13 not diamond cards, which would be 39, which is equal to 3/4. Okay, so we've correctly set the first stage. Now, if we draw again, we're not putting the diamond that we just drew back in the deck. So if we've drawn a diamond, that is gone to us forever. So we have diamond and not diamond again. And we'll call this one A1 intersection A2, and this one will be A1 intersection A2 bar, where A2 represents drawing a diamond in the second stage. So if we don't have any diamond, if we've taken the diamond away, that means the total possible ways we can select a card is now 51, and out of the diamonds that are left, there's only 12. So our probability now of drawing a diamond again is 12 out of 51. This is different from the original probability A1. It's no longer 13 out of 52, it's 12 out of 51 because we've drawn from the total pool and specifically from the diamonds. If instead we're drawing from the not diamonds, then we're picking out of the 39 that are not diamonds, but we still are only picking out of 51 total. Similarly, by the way, those fractions don't reduce, so we'll leave them that way. If we do this again, so A1 bar has occurred, and we're interested in A2, or A1 bar has occurred and we're interested in A2 bar, which again represents either first we drew not diamond and then we draw diamond, or not diamond and not diamond again. So in both instances, we again have some fraction out of 51 because we have not put that original card back. The difference here is the original card was not a diamond. So when we go to select a diamond, we were taking out of the original 13 diamond cards. And that means if we're selecting not diamond, there was already one that wasn't there. So instead of picking out of 39, we're picking out of 38. And you should check that this makes sense by adding these two fractions, and you should get 1. So our difference here is, what's the probability of drawing 2 diamond cards? Well, same principle applies. It's the general form of the multiplication rule. So probability of A1 intersection A2 is the probability of A1 times the probability of A2 given A1 has occurred. And this probability is not the same as just the probability of A2 because it actually does depend on what happened with A1. So the selection of the first card impacts and affects the likelihood of the selection of the second card. Then we have 13 out of 52 times 12 out of 51. And you can simplify that, and you should get something along the lines of 0.0588. So roughly a 5.8% chance of drawing 2 diamond cards in a row.